I'm going to integrate from one end to the other of the rod. My y can come outside, I don't need to keep it inside. And I'm left with dx over x squared plus y squared to the 3/2. And that's in the j direction. So all I have to do is integrate these. It's really no big deal. Now, here's where just the experience of practice comes in. If I'm centered in the middle of the rod, and the rod is perpendicular, and so equally symmetric on either side, then I can infer right off the bat that the x components are going to cancel out. Whatever x component over here that's generated in this direction will be equal and opposite to the electric field x component of the corresponding dq on the opposite side. So if I'm not in the middle of this thing, I have to solve everything. But if I'm in the middle, so that I can take advantage of the side symmetries, the transverse symmetries, if I get the parallel symmetries, transverse symmetries, then it allows me to be able to ignore this by symmetry. So the y component, or the x component, is going to cancel out. So this will sum to 0, or this will, if I'm in the center. So at least it makes the problem a little more manageable. So what I'm left with then is to solve for whatever the electric field is at this particular point. Essentially what I'm doing is I'm taking, now my y comes out again, I'm taking all of this stuff, then I'm multiplying that by the completion of this integral dx over x squared plus y squared to the 3/2 in the j direction. See if I'm leaving anything out. I don't think I am.
What's your bounds here?
I got to put my boundary conditions. Limits of integration. Okay, now I can solve this. And we can do some substitutions. We can figure out how you want to solve it. Easiest thing to do, look in the front of the textbook. Okay? Because it's not a calculus class, I'll assume that you're comfortable enough that you can go to a table and find the appropriate integral to solve. So we look in the front, I think it's the front of the textbook. I memorize the integral. It turns out, and by the way, when we have the exam that will require doing this calculation,
Yeah, it's here.
it will be given. You'll have the table with you, right? Most of you have calculators that will give the integral anyway anymore. So unless I made you all use a calculator like, is it Stephen?
No, Steve. Jeff.
It's Stephen, right?
Jeff.
Jeff. Okay. There's an S in there somewhere. Is it Jeff Spencer?
Yep.
Okay, I knew there was an S. Okay. So, except for Jeff, just about everybody else has a graphing calculator that will probably solve this equation. Right? So I can't assume anything as far as some of you have the way of solving it, some of you don't. So we'll have that thing there. Well, if we evaluate this thing then, going through all of this, what do we get? Look it up, solve it for me. We got all of the pieces. What does this give us?
It's in the table.
It's in the table. Probably in the textbook if you look hard enough. We're left with lambda y over 4 pi epsilon naught, and then the valuation of this
You got
integral.
x on the numerator,
So we're going to have an x.
and then in the denominator you have a squared
So it's y
So
squared.
we have y squared,
times the quantity.
x squared plus y squared to the 1/2, or?
That's right.
Okay.
Yep.
Is it 1/2? Okay. You want the positive direction, yeah? And is that all?
That whole thing is just evaluated from negative L over 2 to L over 2.
And by the way, if we evaluated the other side, the x component, what would end up happening is the one ends up being the negative of the other. So it will cancel out. It's not a bad thing if you wanted to evaluate that first part. Probably a good idea just for the practice of it, but it should, in fact, because of the limits being symmetric, plus or minus, it'll end up canceling itself out. If for no other reason than the sign is anti-symmetric about the x-axis, or I mean about zero. Okay, so plug all of this stuff in. The L over 2 is for the x, the y is the fixed value. And so we end up getting lambda 4 pi epsilon naught, and the y ends up being there on the bottom because it's y over y squared. So we've got those straight. And then we have L over 2 times L squared over 4 plus y squared to the 1/2 power. And I'm going to minus this same quantity. It's negative itself, so it's going to give me 2 of these. And that would be in the j direction. So all of that just sort of reduces to that. Now, aside from doing this calculation, getting a number here, there's something else I want to point out to you when you get the value here, when we get this thing laid out. Okay, so we put this all back together. What does this give us now? It gives us the 2's cancel out, and we're left with lambda L over 4 pi epsilon naught. This does not look pretty on the surface. And then we have L squared over 4 plus y squared to the 1/2, or square root of all that, and that's in the j direction. So it reduces to this. Now it's a plug and chug for the numbers. Here's something that's kind of interesting. Turn down the lights a little bit, put a little Barry White, drink a few beers, so we can't quite focus well. And we look at that equation really, really carefully, kind of squint our eyes so that it's a little foggy. You'll note that if L is small compared to y, this thing reduces to something we've seen before. What would happen if L is much, much smaller than y? What would this reduce to? This is L is much, much smaller than y. This thing reduces to it's lambda L over, this term goes away, so we've got the square root of y squared if this term is tiny compared to this term. So you're left with 4 pi epsilon naught y squared in the j direction. And remembering that lambda is the total charge q over L, this thing reduces to q total over 4 pi epsilon naught y squared j. And y is effectively the separation distance. J is in the direction from the charge to the location in question. This is the electric field for a point charge. Moral of the story, with any net charge system, this was just one example of it, with any net charge system where the dimensions of the charge location, where the charges are, however they're spread out, it doesn't matter how they're spread out. If the dimensions are small compared to the distance where you're looking, everything looks like a point charge. Even a charged rod. If you're far enough away on the other side of a parking lot, a highly charged conducting rod on the other side of the parking lot, assuming that you can measure the field over there, would be a point charge. Because 1 meter into 100 meters is negligible when you square both terms. So everything in its absolute length, spatial limit reduces to a point charge. That's kind of a nice thing to know. Whenever you look at a problem, for instance, where the dimensions of separation, you looked at the first problem, it wouldn't work because you've got plus and minus. But when you've got a dimension like 3 to the negative 4th meters, where the charges are located, but you're looking at a distance of meters away, it's like 2-point charges. So it wouldn't even matter if this was a point, if problem 1 were 2-point charges, or were just 2 smears of charge that had a negative and a positive end equally and oppositely located. It would just look like a point electric dipole, because each of the positive and negative charges, however they were spread out, would still look like a point charge. So everything, any net charge system, looks like a singular point charge from a distance, which is a nice thing. You can save yourself a calculation. If you have to calculate something like this, you can kind of look at the extreme and get a number because this even makes sense. One of those little mental checks. Okay, so I don't know what this number comes out to. You can tell me.
0.4.
Is it 0.4 newtons per coulomb? In the J direction? Honestly, I don't know. I didn't do the calculation. Yeah, it seems reasonable. It's a decent amount of charge. We're not too far away. In this case, it doesn't reduce to a point charge because this thing is a half a meter in length
And only
and only
a third of a meter.
a third of a meter high. By the way, look at the other extreme here. These are sort of the classic things that you point out. What does this reduce to when L is very, very large compared to Y? And we don't even fit in that condition. But what would this look like if L was large, and so we could neglect Y? So if L is much, much larger than the distance away Y, this thing actually reduces to lambda L over 4 pi epsilon naught. Now the Y doesn't go away because that one was explicit. But inside the integrand, L squared over 4 is much, much larger than Y squared. So this then reduces on the bottom. The Y stays there. And we end up with square root of L squared over 4 is L over 2. One of those cancel out, the L cancels out, and we're left with lambda over 2 pi epsilon naught Y. In other words, when you're close enough to this thing, relative to the dimensions, the electric field decreases inversely with how far away you're looking. But when you get far enough away, it decreases as the square, inversely with the square of separation. It acts like a point charge when you're far away. The electric field decreases with Y when you're fairly close. And if you're in the middle, then you've got to use that long, horrible equation to solve for it. But they're all sort of implications. We just look at the limit, sort of a heuristic approach, look at what the extremes are and what does it tell us. Okay, so we got a calculation. Here's the last part, and this is something I wanted you to think about in terms of this electric dipole moment. How much torque would that first dipole experience if you placed it at that 0.3 meter location up above, but had it oriented at a 30-degree angle? How much torque would that be? How much torque would be pulling on that? By the way, lest this seem like really abstract, you know how microwaves work? Basically, you alternate an electric field, and the dipole moments of the water and the protein molecules and the oil, they rotate back and forth due to the torque that's generated by the changing electric field. And as they vibrate, that rotational energy gets translated and transferred into internal energy. It gets hot. But it's because of the electric dipole moments of the molecules in the fluid. So it's basically this problem.
So if certain plates get hotter than other ones.
And that has to do with whatever the material is. If you've got polar molecules in there, OH groups or whatever that might be able to do that. Or even just ionic salts. Right? We use like uranium in the old days. You remember the Fiesta ware, the old orange Fiesta ware? We don't even know what that is anymore. But that's that uranium oxide. It's what produced that old orange color on the old Fiesta ware. It's radioactive. But it's a salt, right? Anything that's like a pigmentary salt, like titanium dioxide that we use in paints and all these things, they got ions that are discretely positive and negative. They're bipolar the way they're arranged in their coating. So when you manipulate that electric field, you get these things doing this, and by doing that, you get a certain amount of energy transfer to the plate itself. It's hard to calculate in a general way, so it depends on the material. So you betcha. So we put this dipole up here. We'll point it this direction. Let me calculate the torque. Calculate the torque. And this one I didn't give you, but I'll tell you what it is. To calculate the torque, you take the dipole moment and do the cross product or the vector product with the electric field. And lest this looks weird, think about what the what the dipole moment is. The dipole moment is Q, and then you've got this separation distance D, which is a vector, so there's sort of a built-in lever with that. And you're crossing that with E. And if you move the Q over there, Q times E is electric force. And you're left with a lever expression, L cross F, which is just your typical torque equation from 211. Or whatever statics, dynamics class that you would take. So that's all it is, but this is the simple calculation to use. In other words, the direction of the electric field is going to be the direction that this thing will tend to rotate toward on the positive end and opposite on the negative end. And the equal and opposite about the center, so they just add up to this. Each of the individual levers is D over 2, but they're equal and opposite in the magnitude, so the halves cancel out. And then just in your minds, I think about the electric field varying with time, like a sine function. Think what would happen to that torque. No, we don't have to do that. But I mean, just that's the microwave effect. Dipole heat. So it got hot in here. It must be the physics. It's kind of fun. So I gave you quite a bit to chew on today. I definitely want you to keep in mind what I was talking about with these limitations.
I think I'm gonna break my teeth.
With these large rod, small distance, small rod, large distance of separation, because as we get into Gauss's law and start talking more fundamentally, we'll be able to derive that expression from a different perspective, which is kind of cool. So, let you guys go. I gave you a lot to